All right. So hi, everyone. I'm Nancy Harris at the World Resources Institute based in Washington, D.C. Thanks for inviting me here to talk a little bit about the work that we've been doing. So I am going to, normally I start with a little bit more um, context, but since I only have 10 minutes, I'm going to get right to the point. So what was the goal of our analysis? That was to create global maps of forest-related greenhouse gas fluxes at 30-meter spatial resolution by combining IPCC inventory methods with the best spatial data that we have available on forests to simulate gross emissions, gross removals, and the net flux of greenhouse gases between forests and the atmosphere. And this work really began back in 2014 when Global Forest Watch funded the Woods Hole Research Center, now the Woodwell Climate Research Center, to create a 30-meter version of a global biomass map. And to do this, they conducted this huge review of published LiDAR-based biomass equations for different regions of the world so that they could then apply them to glass LiDAR shots. JEDI did not exist yet. So using glass LiDAR shots and a model to produce this global 30-meter biomass map. And so the idea back then was that we could then combine this map of biomass in the year 2000 with the University of Maryland's global tree cover loss data to map emissions. And so that's essentially the map that you see here, although in this version, we do include the other carbon pools, including soil emissions where they're relevant. But this kind of activity data times emission factor exercise, we've kind of been doing this for like a decade now, right? So Sasan Sachi and I did this back in 2012. Alessandro and Sasha Tayukovina developed a similar estimate using more of a sample-based approach for the activity data. Frederic, I know that you have produced an estimate of tropical deforestation emissions. So the point is, at this point, it's pretty safe to say that if we multiply tree cover loss by biomass, we will get roughly the same pan-tropical answer. We get a tropical emission estimate of somewhere between 1 and 2 petagrams of carbon per year. We have a pretty good consensus on that now. And so for years at Global Forest Watch, we'd then be getting this question from the policy community of, okay, GFW, when are you going to map global emissions and not just tropical emissions? And so technically we had this global biomass map. So in theory, we could have published this emissions map a long time ago, but we knew it was not going to go over that well because what we've ended up with here is 2 distinctly different carbon monitoring systems for the world, right? We have tropical deforestation emissions derived largely from remote sensing data. But had we published this map for the world, I guarantee we would have been accused of spreading misinformation about the status of northern forestry and providing alternative facts. And I'm borrowing a term from the Trump presidency. And that's because that emissions map that I just showed, we do not show the carbon removals that are occurring in forests all over the world. So all those dark green areas of primary forests, secondary forests, mangroves along the tropical coastlines, forests that have regrown since the year 2000, shown in blue. Over the years, we've been getting better and better data from remote sensing to map the emissions side from tree cover loss, but the policy community still had no information about the carbon removals side of things, what carbon removals were happening in forests that were not being cleared. And part of the reason we couldn't map carbon removals is because the forest monitoring that happens up in the northern countries generally relies a lot less on remote sensing, right? And more on the remeasurement of national forest inventory plots, which do capture those carbon removals, but the data are not accessible in a format that the policy community can really digest. So if we look at this chart, Sasan alluded to this a little bit earlier, this difference between the stock change and the gain loss approaches. So the red plus MRV world that's being set up in the tropical developing countries, they're focused on the loss of carbon stocks from deforestation. So I show those here in red. It's the loss side of the IPCC gain loss approach. But in developed countries, the monitoring systems are generally more reliant on these periodic inventories, which capture the net change in carbon stocks. But those are not broken down into gains and losses or carbon removals and emissions. So our question for this analysis really became, how are we going to put carbon removals on the map? We've got the emissions side down, but what about the removal side? So to get this started, we stratified global forests using various published map layers and then paired those with removal factors that we developed from a number of different data sources. And for some strata like mangroves and primary forests, we relied on tier 1 default removal factors from the 2019 IPCC refinement. And then for other strata, we had better information. Like for example, young secondary forests, we worked with Susan Cook-Patton's team at the Nature Conservancy to develop a global map of natural carbon removals from natural forest regrowth. So it's really kind of a mixed bag of data that we're using to piece together this removals map. And this is what we get in the end. It's definitely not as spatially detailed as the emissions map that I showed, but I guess the upside is that we now have a map of carbon removals that exists separately from the emissions map. And so as a result, we can now subtract one from the other to map net annual greenhouse gas fluxes. And this is really important for the policy community because the interventions that we designed to reduce emissions from forests, they're going to be a lot different, right, from those that we designed to increase carbon removals. So we need to start monitoring both of these terms separately rather than monitoring only the change in the net flux as has been the status quo. And because this tree cover loss data that we have on Global Forest Watch are annual, we can break down emissions by year and see that globally emissions have increased from less than 5 billion tons of CO2 per year to more than 10. For some perspective, we also show, the emissions from the 3 largest country emitters. So it's important to note here that these emissions estimates include all forms of forest disturbance, deforestation, fire, forest harvest, et cetera. Basically anything that's picked up by the UMD loss data. But we can't really investigate that time trend in the removals or the net flux estimates because we don't have annual data. So we estimate instead a 20-year average net flux of about 7.6 gigatons of CO2 per year absorbed by forests from the atmosphere every year. Our results are shown on the right, and then for comparison, the bar chart on the left shows the sink as derived by the Global Carbon Project of about 6 gigatons of CO2 per year. One thing I want to flag quickly before I wrap up here is how we address uncertainty for this analysis, and that helps guide our thinking on how we can improve this monitoring framework going forward. This table shows the different components of model uncertainty in the columns, and then the rows show the final model outputs of gross and net fluxes. And the values in the cells, those show the percent reduction in output variance as we bring the variance of each of those individual model components down to 0. And so when we do this, we can see which uncertainty terms are really driving the overall uncertainty of the final output maps. We have this broken down by climate domain in the paper too, but here I'm showing the global results. And you'll notice that for gross emissions up in that left red box, the variance of the emission factor term is actually driving more of the uncertainty than the activity data term. And then the other box on the right, for both gross removals and net flux, the variance of the removal factor for old secondary forests is far and away the most important source driving this huge uncertainty of the entire analysis. And so the question is what is driving that giant number? And that's due to our use of the tier 1 default removal factors for temperate continental and mountain forests outside of the United States and Europe, where we're using better data. But these tier 1 values were revised in the 2019 refinement, and we're now working with the Forest Service in the US to kind of revisit these giant standard deviation values to make sure that they're derived correctly. Okay, so just to sum up what's new here, first, it's a brand new methodological approach. For one, we haven't really had anything resembling these global maps before, and certainly nothing at the spatial resolution of 30 meters. And so that helps users of the data to better understand how their local forests are contributing to the global climate. We're also mapping all forests and all carbon pools, and so therefore attempting to do full forest carbon accounting. So regardless of whether they're managed or unmanaged forests, some inventories report only for the forests that they consider managed. And then finally, this analysis gives us improved attribution to the where and the why of forest carbon. We also use the same driver's map to disaggregate the fluxes into those different colors. And then finally, the policy implications. It's pretty clear that we need to leverage all possible options on the table to mitigate climate change. And so for forests, that means we need to reduce emissions and also increase carbon removals. And we now have a framework for tracking greenhouse gas fluxes from forests at scales that are more relevant for informing climate policy. And this framework that we set up provides opportunities for enhanced coordination between the science community and the policy community. But I will be the first to admit that this framework is also a sort of a first draft. There's a lot of room for improvements here. And so we can use that uncertainty analysis I talked about to help prioritize the data improvements we need to eventually get those uncertainties down. And so I think that's it. If you have any questions, happy to take them at the end or